The famous Atwood law states that any application that can be written in JavaScript will eventually be written in JavaScript. People laughed at the idea of using JavaScript everywhere at first, but these days, when we get so much vibe-coded slop, having the opportunity to work on a good old human-maintained JavaScript codebase sounds like the dream job. What's interesting is that there is a new lore emerging in the web dev space. So while all applications will end up being written in JavaScript, all JavaScript tools will end up being written in Rust. After major projects like Bun or the Vite ecosystem adopted Rust in the past months, the Facebook team just announced that they migrated Flow from OCaml to Rust as well. Rust is quickly becoming the language behind the language powering the web, and the Flow migration story explains exactly why more developers are preferring Rust these days. If you are not familiar with it, Flow is Meta's static type checker for JavaScript. It was originally released before TypeScript became the obvious default, and for years it was one of the serious attempts to make large JavaScript codebases safer without abandoning JavaScript itself. In all honesty, picking up Flow today would be kind of a bad idea considering TypeScript's dominance, but it is still a very interesting project since Meta still uses it internally and React's own source code is Flow-typed. Flow was originally written in OCaml, which makes sense historically since the language is excellent for compilers, type systems, parsers, and language tooling. A lot of smart people love it for very good reasons, but the problem is that great language design does not automatically give you a great ecosystem, great tooling, easy hiring, or smooth integration with the rest of the modern JavaScript infrastructure. And this is basically where Rust entered the picture. According to the Flow team, they first considered rewriting Flow in Rust all the way back in 2019 because Meta's internal JavaScript monorepos were already creating serious scalability problems. But at the time, a rewrite looked too risky because it would take too long, the payoff was uncertain, and the team expected the scalability problems to hit before the rewrite could realistically be finished. So instead of rewriting everything, they focused on architecture work like types first, and the Rust idea was put on hold for years. But in 2025, the surrounding environment changed. Inside Meta, Firefly, which is basically the Rust rewrite of Pyre, delivered more than a 30x performance improvement. During this time, outside Meta, the TypeScript team announced their native Go port, with Microsoft claiming around 10x faster performance compared to the JavaScript implementation. So, suddenly, these big language tool rewrites stopped looking like crazy engineering vanity projects and started looking like the obvious direction for serious developer tooling. Let's be honest though, developers are famous for rewriting their startup ideas and pet projects in newer, cooler languages, only to get bored halfway through and abandon the whole thing. Back to Flow, the team actually considered safer options like Go or Kotlin. And in some ways, those would have been easier ports because OCaml, Go, and Kotlin all use garbage collection, which maps better to the memory patterns of a compiler or type checker. Rust was the harder option because you move from a garbage collected world into ownership, borrowing, explicit allocation decisions, and all the painful parts that make Rust a famously difficult language. But the team wanted more than just a larger ecosystem. They wanted Flow to integrate better with the modern JavaScript tooling stack, where projects like SWC, Rolldown, Biome, and parts of the Vite ecosystem are already moving toward Rust. So if they were going to pay the cost of leaving OCaml, they wanted to do it once and land in the ecosystem where JavaScript tooling seems to be going. The second important decision is that this was not a rewrite in the fun architectural sense. It was mostly a line-by-line port, which is actually pretty common because it is by far the safest approach possible. Flow is a mature type checker used across massive internal meta codebases, so changing its behavior while rewriting it in another language would be a great way to make apps like Instagram even buggier than they already are. And, of course, a complete rewrite would have been more exciting, but it also would have created a much harder rollout because every behavior change would have to be separated from every porting mistake. So they chose the conservative path to keep the behavior, port the implementation, and deal with deeper design improvements later. Now, we get to the part you guys probably suspected from the get-go. Of course, the port was heavily assisted by AI. The team used this approach because a mechanical port is exactly the kind of predictable work where LLMs can be useful. Basically, you ask an agent to port a function while preserving the behavior, then you compare it with the old implementation. It is a boring process that doesn't require any creativity. And this is important because they explicitly rejected AI changes that took too many liberties because the goal was not to generate beautiful Rust. The goal was to preserve Flow. If that sounds familiar, it is because Bun went through a similar rewrite a couple of months ago, and their approach was identical. The parser was the first big test. One engineer ported the entire parser with AI assistance, got all tests passing, and ended up with around a 2x performance improvement in about 4 weeks. That early result was strong enough to justify moving forward with the full port. After that, the team spent about a month porting the systems needed for the checker, ranging from module resolution to dependency analysis, type signature extraction, and the other pieces that sit around the actual type checker. The checker itself was the actual hard part. By that point, AI models had improved enough that the team could use agent teams instead of manually asking for a few functions at a time, but they still kept strict controls. Reviewer agents checked the output against project guidelines, and some of the ported Rust code temporarily included the original OCaml as comments, so it was obvious when the port stopped being line by line. And then, when the first full check pipeline ran, exactly 0 tests passed. But because the port was intentionally mechanical, debugging became local. So the team could compare the Rust behavior against the OCaml behavior and fix differences one by one, and within a week they got the checker tests passing. Another interesting detail is that they did not freeze development on the OCaml version while porting to Rust. Normally, keeping 2 implementations moving at the same time is painful because very new OCaml changes would need to be manually duplicated in Rust. But because the Rust foundation was already in place, porting new changes became much easier. So the team could keep shipping features while asking AI agents to port the equivalent changes to Rust. Of course, the first complete Rust version was not magically faster. In fact, after the checker port was complete, the Rust implementation was still significantly slower than OCaml in some cases. This is the less glamorous part of Rust migrations. Rust gives you control, but control also means you can make bad allocation decisions very easily. The team found big O problems, memory issues, and performance regressions. Some were obvious enough for AI agents to find, while others required human insight, like improving the work stealing scheduler or noticing repeated computations that had accidentally been introduced during the port. They also had a specific problem caused by using Rust patterns like RC and refcell heavily, which is basically what happens when you port OCaml 2 literally into Rust. It keeps the migration realistic, but it can also create reference cycles and memory pressure. Some of the fixes involved manually breaking those cycles. The final result is that on Meta's huge internal JavaScript codebases, the new Rust implementation is generally around 2 times faster across most type checking stages and between 30% and 100% faster in the most computationally expensive checking stage, which is quite impressive. And before wrapping things up, here is your awesome trivia of the day. While Rust is a powerhouse today, and it is able to replace languages like OCaml, OCaml was actually the language powering the first versions of Rust. Graydon Hoare started Rust as a personal project in 2006, and the first compiler he wrote for it was in OCaml. Mozilla picked the project up a few years later, but that original bootstrap compiler stayed in OCaml until Rust got mature enough to compile itself around 2011. If you like this video, you should consider joining our community where I'm posting more dedicated weekly content. Please don't forget to smash all the buttons, and until next time, thank you for watching.